Up to this point, we've been relying on the assumption that we have a sample size of greater than 30 when we do a hypothesis test, which is one of the conditions that allows us to use the normal approximation, to use z-scores in the z-table to find out if we have a statistically significant result. In this lecture, we're going to talk about what happens when we have small samples that we want to do inference on. There is a superstition in some parts of the world about Friday the 13th that says that Friday the 13th is an unlucky day. It's a day when bad things are more likely to happen to you. So some researchers in the UK wanted to know if there are differences in how people behave and outcomes for those people on Friday the 13th as compared to other days. So they collected some data on traffic flows, on traffic accidents, and on hospital admissions on days that are Friday the 13th in different months in these years from 1990 to 1992. And as a point of comparison, those same variables on the previous Friday, so Friday the 6th in each of those months. So below is an excerpt from this data set where we're looking specifically at traffic flows, so traffic flows on the 6th and traffic flows on the 13th. And an assumption that we're going to make as we analyze this data is that traffic flow on a given day at these different locations is independent. So we might want to know if people act differently on a day that's Friday the 13th as opposed to a day that is Friday the 6th. And one way to try and get at that question is to compare traffic flows on these 2 days. So we might set up the following hypothesis test, where the null hypothesis says that average traffic flows on Friday the 6th and on Friday the 13th are equal, and the alternative hypothesis says that average traffic flows on Friday the 6th and the 13th are different from one another. So each case in our data set is going to represent traffic flow at the same location in the same month of the same year. So one measure on Friday the 6th and the other on Friday the 13th in the same location. So are those two counts independent of one another? So remember that a useful way to think about independence is whether having information about one of your variables gives you something useful to say about the other one of your variables. So if you have information about what traffic flows are like on Friday the 6th in a particular place, does that give you useful information about what traffic flows are likely to be like the following week in the same place? Probably so. If you have a regular commute, you're probably pretty good at predicting how heavy the traffic is going to be at different parts of the day so that you know how to plan your commute. And that is because traffic flows are going to be relatively similar week over week in the place where you live. So traffic flows are related to the location of the particular road, all of the businesses and residences in that area that affect where people are going and the paths that they're likely to take. So traffic flows on Friday the 6th and Friday the 13th are not going to be independent of one another. They're very closely related. So what we want to know is if on average there is a difference between traffic flows on Friday the 6th and Friday the 13th. So we need to specify hypotheses to figure out the answer to this question. So go ahead and take a look at these 4 sets of hypotheses and decide which is the set that we need to test. So the correct answer is C. We are interested in whether the mean for Friday the 6th and the mean for Friday the 13th are equal or not equal, like the hypothesis set A suggests. But remember that we want to take the difference between those means in order to center our null distribution around 0. So we want to test if that difference is equal to 0 or different from 0. This is something that we talked about in our previous lecture and that your textbook covers as well. The next step in our hypothesis testing approach is always to check our conditions for inference. So the conditions that we've been operating on so far are those of independence, skew, and sample size. So independence, again, is something that we get when we randomly sample from the population and when we make sure that our sample size is less than 10% of the population. In this problem, we were told to assume that these rows were independent from one another, so we're going to go ahead and consider that condition satisfied. We also want to know if our data are skewed. Now remember, we only have a couple of observations of traffic flows, and so we can plot them out on a histogram, and it's a little bit hard to tell what the actual distribution of the data is when we have so little data. So it doesn't look as though there is extreme skew in the histogram, but this is something that we would want to pay attention to because it's possible that there is skew that we are just not seeing. And then the final condition is sample size. We have been talking about the rule that you should have a sample of more than 30 if you want to use a normal approximation to the data. We have a sample size of only 10, which is substantially less than 30. So what should we do when we have such a small sample size? How can we make inferences about the question that we're interested in? Well, we know that we can't use the normal approximation because we don't meet this condition of a sufficiently large sample size. To understand what this means for us, it's important to go back and think about what the purpose of large samples is. So, as long as we have independent observations and not an extremely skewed population distribution, when we have a sufficiently large sample, we know that the sampling distribution of the mean is nearly normal, and that our estimate of the standard error is reliable. So our estimate of the standard error comes from our sample data. It's the sample standard deviation divided by the square root of the sample size. And this is our estimate of the population standard error, which is the parameter sigma in the population divided by the square root of the population size. So because we don't have access to population data, we have to approximate that using our data from the sample. And we know that when we have a sufficiently large sample of 30 or greater, our estimate of the standard error is likely to be really reliable. But when we have a small sample, that estimate is much more likely to be way too high or way too low or just problematic. And that's a problem because a standard error is fundamental for the inferences that we make. Standard error goes into our formula for the confidence interval, it goes into our calculation of the z-score, and so if we have an incorrect standard error, we're very likely to make bad inferences. I want to briefly talk about one special case where even with small samples, we can be pretty confident in our assumption of normality. So in general, the central limit theorem says that when we have sample sizes greater than 30, the sampling distribution of the sample mean will be nearly normal, no matter what the shape of the population that we're drawing from is. So even if we have skewed underlying population distributions, the sampling distribution of sample means will be nearly normal if we have a sufficiently large sample. The central limit theorem also tells us that if the population distribution is nearly normal, that even when we have very small samples, the sampling distribution of the sample mean will be nearly normal. So this is just a slightly different way of thinking about the central limit theorem. If we have this particular population condition where the population distribution is nearly normal, then the sampling distribution of the sample mean is also going to be nearly normal, even when we have tiny samples. So this is a useful special case to think about, but when we have small data sets, when we only have, for example, 10 observations, remember that it's really hard to try and understand what the distribution of that data is. So it can be hard to think about whether our underlying population distribution actually is normal or not if we don't have more data. So if you have a really good reason to believe that your underlying population distribution is nearly normal, then you might be comfortable making this assumption of normality and going ahead with the standard z-score testing approach that we have been using, but that's something that you should use a lot of caution about. So when we are working with a small sample and we're not going to be basing our inferences off a normal distribution, we're going to instead be working with another distribution called the t-distribution. So this is just another distribution of data, another way that data can be spread out, just like the normal distribution or the binomial distribution or anything else. And this distribution is bell-shaped, similar to the normal distribution, but it has fatter tails, thicker tails, so data are more likely to fall farther away from the mean than they are in the normal distribution. So because in the t-distribution, observations are more likely to be beyond 2 standard deviations away from the mean in either direction than they are in a normal distribution, those tails of the distribution become thicker. And the t-distribution The shape of the t-distribution is based on the sample size. So the sample size is directly related to how thick the tails of the distribution are. And this turns out to be a useful way to help us deal with this problem of unreliable estimates of the standard error in small samples. So a t-distribution has this bell curve shape that should be familiar, and just like the standard normal distribution, or the z-distribution, the t-distribution is centered on 0, so 0 is its mean. And the shape of the t-distribution is determined by this parameter called degrees of freedom, which we're going to define in a little bit. You can see in this graphic on the slide a couple of different examples of t-distributions with different degrees of freedom. So the paler lines have lower degrees of freedom, and as the lines get darker, you can see that the t-distribution gets steeper and the tails get thinner, right? So one of the characteristics of the t-distribution is that it has fatter tails than the normal distribution does, but as degrees of freedom increase, those tails are going to shrink down a bit, and you're going to have more height in the middle of the distribution. So what is happening to the shape of the t-distribution as degrees of freedom are increasing? Well, with higher and higher degrees of freedom, the t-distribution is looking more and more like the normal distribution. And that's the interesting thing about the t-distribution, is that it is most different from the normal distribution when it has really few degrees of freedom. Degrees of freedom are going to be related to the amount of data that we have. So when we have little data, the t-distribution is going to be squatter with fatter tails. And as we get more and more data, and therefore more and more degrees of freedom, the t-distribution is going to converge toward the normal distribution. So as you've probably guessed, we're going to be using our traffic example to illustrate how we use a t-distribution. So let's go back to looking at this data for just a minute. So in this data set, we have information on traffic flows on Friday the 6th and Friday the 13th for these 10 different observations. So we are going to create this difference variable, which is the traffic flow on the 6th minus the traffic flow on the 13th. So the mean of the difference variable is 1,836. The standard deviation of that variable is 1,176. And again, we have a sample size of 10. The way that we calculate our test statistic when we use the t-distribution should look familiar to you. It is our point estimate minus our null value divided by a standard error. So that is exactly the same as the test statistic for a z-distribution. An important difference is that the way that we use that test statistic is dependent on degrees of freedom. So degrees of freedom for the t-distribution is equal to n minus 1, so our sample size minus 1. So when we look at our traffic example, remember our point estimate is this difference, the mean difference in traffic flows between the 6th and the 13th, which was 1,836. Our standard error is going to be the standard deviation we found divided by the square root of n. So that's 1,176 divided by the square root of 10, which is equal to 372. So we can fill out this formula for the t-statistic and take our point estimate minus 0, the null value, divided by our standard error, which is equal to 4.94. And our degrees of freedom is equal to 10, the sample size, minus 1, so 9 degrees of freedom. We are going to use that test statistic of 4.94 to find our p-value. So we can calculate this p-value in R really easily. We're going to use the PT command. So this is a probability under the t-distribution. That's kind of what that stands for. So the PT command is going to give you the area under the t-distribution curve in one tail. So again, you have to keep in mind whether you're doing a one-tailed or a two-tailed hypothesis test. We're doing a two-tailed hypothesis test. So we want to look at the extreme edges of this distribution to the left and to the right. So we're using the PT command. The first argument is the test statistic we found, 4.94. Then we need to specify the degrees of freedom that we have, so 9. We use this lower tail equals false command to tell our, if we want to find the area in the small part of the curve, or if we want to find 1 minus that, so the lower tail equals false is what we want. And again, we're multiplying that by 2 because we have a two-tailed hypothesis test. So that is going to give us this answer of 0.0008. We can also find this p-value using a t-table. Just like we would look up in a z-table, now we're going to use a different table for the t-distribution. So here is what a t-table looks like. So I want to draw your attention to a couple of things. In this far left-hand column, we have a whole bunch of numbers counting up from 1 that are going to represent degrees of freedom. So you're going to want to be looking at the t-table using the correct number for degrees of freedom for the test that you're doing. In the top row, we also have different p-values associated with one-tailed and two-tailed tests. So you need to know whether you're doing a one-tailed or two-tailed hypothesis test to be able to get a p-value from this distribution. And in the middle, we have a whole bunch of different critical values. So remember that when you have larger test statistics in a z distribution, that means that your results are more unusual and therefore more statistically significant. When you have a really large critical value in the z distribution, that means that you have evidence to reject the null hypothesis. This is the exact same logic that we're going to use in the t distribution. So for example, let's say that you're looking at the row for 3 degrees of freedom. So find that on this t-table. And then if you got a test statistic of 1.64, that is associated with a p-value for a two-tailed hypothesis test of 0.2. Now move over to the next row. If you get a larger test statistic of 2.35, that's associated with a p-value of 0.1 in a two-tailed hypothesis test. Now if we go all the way out to the last row, if you got a test statistic of 5.84, that would be associated with a p-value of 0.01 for a two-tailed hypothesis test. So in the middle of the t-table are sort of what you can think of as cutoff values for different p-values at different degrees of freedom, and of course depending on whether you're doing a one-tailed or two-tailed hypothesis test. So let's consider how we would use a t-table to find a p-value in our particular example. So recall that we have 9 degrees of freedom. Our sample size is 10, we subtract 1 and that gives us 9. And we found a test statistic of 4.94. So we're going to be looking at the row for 9 degrees of freedom. And if we follow that all the way out to the right, we can see that a value of 3.25, a test statistic of 3.25, would be associated with a two-tailed p-value of 0.01. So a test statistic that is greater than 3.25 is going to have a p-value of less than 0.01. So our test statistic is 4.94. It's greater than 3.25. And so we're going to have a p-value that is less than 0.01. Now remember, when we did this in R, we found a precise p-value of 0.0008. So if we use R, we can find the actual p-value that corresponds to the test statistic that we find. If we use a t-table, we can make a relative statement. We can say that our test statistic is corresponding to a p-value that's less than 0.01. So given this finding of a small p-value, what can we conclude from our hypothesis test? Well, remember that really small p-values give us evidence to reject the null hypothesis. So the data give us convincing evidence that there is a statistically significant difference in traffic flows on Friday the 6th and Friday the 13th. So even with very little data, we can be pretty confident in this finding that the traffic flows are different. And in particular, we found a positive point estimate, which means that traffic flows are heavier on Friday the 6th compared to Friday the 13th. So we have our point estimate, but of course we want to also have a margin of error around that estimate. So how exactly can we go about finding the specific difference between traffic flows on Friday the 6th and Friday the 13th, and how can we construct the confidence interval around that. So confidence intervals are always going to take this form of a point estimate plus or minus a margin of error, and a margin of error is a critical value times a standard error. So we're going to use critical values from a t-distribution, not from a z-distribution. So remember, in a z-distribution we have a 95% critical value of 1.96. The critical values are going to be different when we look at a different distribution of data. So we're going to have to go to a t-table and find critical values for the t-distribution that correspond to the level of confidence that we would like to have. So to find our critical value, we need to know three things: how many degrees of freedom we have, whether we have a one-tailed or a two-tailed hypothesis test, and what our desired level of significance is. In our example, we have 9 degrees of freedom, we have a two-tailed hypothesis test, and we want to find a 95% confidence interval. So for a 95% confidence interval, we want to go out to the significance level 0.05 for a two-tailed hypothesis test with 9 degrees of freedom. So if we do that, we can find our critical value of 2.26. So that is the critical value for a t-distribution with 9 degrees of freedom for a 95% confidence interval in a two-tailed hypothesis test. So in this particular t-distribution, with 9 degrees of freedom, 95% of the data is going to fall between negative 2.26 and positive 2.26 in this distribution. Okay, so 2.26 is the critical value that we're going to use. Now let's go ahead and construct our confidence interval. We have all of the information that we need to calculate the confidence interval, so go ahead and take a look at these different options for equations for calculating that interval and see which one you think is going to give us the right answer. To calculate this, we take our point estimate plus or minus the critical value that we just found times the standard error. So that's going to end up giving us a confidence interval from 995 to 2,677. So what that confidence interval tells us is that with 95% confidence, traffic flows on Friday the 6th are greater than traffic flows on Friday the 13th, with a lower bound of 995 and an upper bound of 2,677. So we don't actually know what the units are for traffic flow, so the substantive interpretation of this isn't something that we can figure out right now just based on the information from this example, though I'm sure that the researchers who did this study specified those units in their paper. But regardless, we can say with relative certainty that traffic flows on the 6th are greater than traffic flows on the 13th, and this is the confidence interval around the point estimate that we have for that difference in flows. So let's just recap what we did here. We have a sample that is less than 30, and if that's the case, then sample means are going to follow this t-distribution with a standard error that's equal to the standard deviation of the sample divided by the square root of n. We're still assuming that our observations are independent of one another and that we don't have extreme skew in our data. We are going to calculate our t-test statistic as the point estimate minus the null hypothesis value divided by the standard error. And we're going to have the degrees of freedom of our t-distribution be equal to the sample size minus 1. And as always, we're going to calculate the confidence interval as our point estimate plus or minus a critical value times a standard error. And those critical values are going to come from the t-table. So in the past 2 lectures, we covered analysis of paired data and how we find a difference between sample means. You might have noticed that the example that we looked at in this lecture was also about paired data, just a situation where the data that we're analyzing only has 10 observations in it. So we took a difference between traffic flows on Friday the 6th and Friday the 13th, and we used that difference variable in our analysis. So anytime we're working with just one variable, but we have little data, we can use this approach as long as our conditions about the independence of our observations hold so that we can use our t-testing approach. We can also expand this approach and do inference looking at the difference of two small sample means. So if we are looking at the difference in means between two samples, and one or both of those samples is small and less than 30, we can also use the t-distribution approach to analyzing that data. So if we're looking at the difference in means between two small samples, we're going to need to use this particular standard error formula. This is the same formula that we use when we are looking at the difference in means for samples of any size, the standard deviation of one sample over the sample size for that sample, plus the standard deviation of the other over the sample size of the other, and that's all square rooted. There are some conditions that we need to take into account. We need to have independence of observations within our two groups, as well as independence of observations across those two groups. So those are conditions that we talked about in the last lecture. And of course, this is the approach that we're going to be using if one or both of our sample sizes is less than 30. We also want to make sure that neither distribution is extremely skewed. So to do the hypothesis test, we're going to calculate our t-test statistic by taking the point estimate minus the null value divided by the standard error. The degrees of freedom for this test is going to equal the minimum of the first sample size minus 1 or the second sample size minus 1. So you calculate both of those, the first sample size minus 1 and the second sample size minus 1, and whichever one is lower is the degrees of freedom for your t-distribution. And then you calculate your confidence interval by taking your point estimate plus or minus a critical value with the correct degrees of freedom times the standard error that you calculated. And that is the hypothesis testing approach for this situation where you have small samples and you want to find the difference in those means. So that brings us to the end of our lecture on doing inferences in small samples. Thank you for listening, and I'll see you next time.